The previous video used a simple algebraic way to derive the Dirac equation directly from the Wise oscillation, circumventing the Klein-Gordon equation. When also avoiding Dirac's use of the imaginary number, it resulted in an alternative version having 8 components instead of the regular 4. The reason for further going into this is the idea that the way an equation is derived says something about its meaning. A derivation shows the physical concepts that one has to put into the equation. So having another derivation shows something extra about the equation. This video starts with a comparison of the two approaches. The first differential equation of the alternative version was that for the stationary de Broglie oscillation, which for a particle moving in the x direction was extended to the one shown. The essential point to notice is that it is linear in the energy and momentum terms that are equivalent to the operators. Only in the next step, the quadratic relation of relativistic invariance was included, giving this combination. And this one is equivalent to the regular Dirac equation. Take Py and Pz is 0 in that, and you get the same one as above for the combination Ψ1, Ψ4 and Ψ2, Ψ3. So the two approaches are each other's reverse in this respect. Dirac makes the quadratic Klein-Gordon one linear, and the alternative one makes the linear one quadratic, both coming to expressions like equation 2. So over to the next step, which for the alternative is this one. And that of Dirac is this one. So for this step, the two approaches differ. But for the next one, they are conceptually the same again, here shown for the alternative. And here for the Dirac version. The number of components differs due to the previous step, but the operation is the same. To double check everything, the Dirac version is rewritten as shown, giving one of the familiar versions of the Dirac equation, so the calculations so far are correct. Now what does all this mean? For the standard Dirac equation we have the connection with spin and spacetimes through the matrices used to construct it. So to continue the comparison, let's make the alternative one more similar by turning its algebra into matrices. These ensuing D matrices are the same as the first and third Pauli matrices. Their anti-commutativity represents the requirements of including CPX in the energy relation. Now for the other directions similar matrices are constructed, using these two easily proven rules. Probably other choices are possible, but this series is just to show that alternative equations are possible. This is the final result. Now we can make a comparison with the standard Dirac equation in terms of their matrices. So the new Q matrices have a form comparable to the standard Dirac alpha matrices, but with double the dimensionality and with the 4-dimensional T taking the place of the 2-dimensional sigma. Notice that the alpha 1, 2, 3 of the regular one that correspond to x, y, z has their commutation relations determined by the Pauli sigmas. The Pauli sigmas obey these commutation relations, representing the SU2 properties of spin is 1/2, whereby the Dirac equation describes the corresponding particles. The epsilon is the well-known Levi-Civita symbol that takes care of the permutation of indices. So let's look if something similar applies to the Q's. The matrices that have the position corresponding to the sigmas are the T matrices, which when written out explicitly have the form shown. And these are their commutation relations, with the place of the I taken by IT. So there is a difference, but also a similarity. Here's the similarity. So how about the difference? In order to highlight the similarities and differences, especially in dimensionality, we will adopt a special notation, also to avoid the difficult to read Kronecker version. With these definitions, the multiplication of matrices of different order can be executed like multiplication by a number. Here's the first application of the new notation. It shows that where the 4-dimensional Dirac equation has 2 spinors and spins, with the new 8-dimensional versions this seems to be doubled again. So back to where this difference in doubling happened. The program of Dirac was to split quadratic relations into linear ones following this basic method, with the alpha and beta being matrices, which then must be anti-commuting and square to unity. Now if one limits this to 2 dimensions and real values, these are the only solutions, the same matrices as those that are the basis of the alternative method. So in effect, what Dirac did for the x and z direction is identical to the alternative method, which was to couple the momentum in the x, y and z directions with the mass term through Lorentz invariance. But Dirac coupled the y direction to the x using the second polymatrix, which is imaginary, which matrix becomes a factor in a differential equation. So its solutions get an imaginary part in the phase. And imaginary numbers in the phase are the representation of rotations or oscillatory functions. So here's the difference between the two approaches. The alternative one uses Lorentz invariance for 3 dimensions equally, and the Dirac version uses Lorentz invariance for 2 of them, and rotational invariance for the third. However, because the alternative treats the 3 spatial dimensions equally, one might suspect that it also hides a rotational symmetry, which we will try to unlock next by reconstructing the commutation relations. So we construct new matrices U from the T by absorbing the IT, and these U already almost obey the sigma commutation relations. Their main problem is that they square to -1 because IT does so. So redefine U while also absorbing the minus sign. So the new U obey the commutation relations of the sigmas. They reintroduce the imaginary constant, however now not for 1 but for all 3 spatial dimensions, so these remain treated equally. Historically, when Wolfgang Pauli was busy describing spin with 2-dimensional matrices, he probably also first found the 2 real ones, while in the commutation relations the third one is their product. But his product squares to -1, so he had to introduce the I in this one, whereby the I also enters the commutation relations. Our need to introduce 3 times I in the 4-dimensional case is equivalent to this. Writing out the U shows this explicitly. Now doesn't look that nice, or in the language of Paul Dirac, mathematically beautiful. To complete the picture, here's the corresponding set of matrices for the Dirac equation in the new notation. Notice that the order 4 submatrices commute, and that the anti-commutation again lies with the 3 sigmas. And that the sigma 2 has reappeared, but now not because it was put into the equation beforehand. To help the discussion on what all this means, here are the spatial matrices in their different representations. Notice that there is no difference between the alpha and gamma matrices as far as their spatial symmetry properties are concerned, both being those of SU2. For the U and Q goes that they are still based on the sigmas, but with differences in order and at the level 4 matrices. So where the alternative 8-dimensional equation also seems to contain a rotation symmetry, there is a difference with the standard Dirac equation. And when viewed from the standpoint of relativity theory, there is a problem, as shown by these equations, which are the fundamentals of relativistic spacetime. You cannot give a place of preference in the order of operations to any of the spatial coordinates. They should be treated equally in all respects. But on the other hand, the regular Dirac equation does correctly describe the states of the electron in any interaction. From the above, it is abundantly clear how these differences are expressed. They lie in the matrices involved. So the associated fundamental questions are, how do these matrices do that, and what is the relation with the physics involved? The primary mathematical answer to the first one is, they couple factorial components. And the primary expression physicists use for the second one is symmetries. And here are some of their expressions of these words and concepts in imagery. Specifically in trying to visualize what constitutes spin is 1.5, the characteristic of the particles that the regular Dirac equation describes. Also showing that this is all about rotations and inversions. The main conclusion is that the Dirac equation is not such a fixed thing as it is usually considered, and that there is room for alternatives and possibly enhancement. At which point this video is put to an end, more or less following the rule of introducing one change in fundamentals per installment, or at least as few as possible. The assessment of the Dirac equation will be continued in another video that starts with a focus on symmetries and matrices. In the meantime, any corrections or additions are greatly appreciated, as is any critical comment.